Right, welcome back. We're starting a little early than I mentioned. So, what I thought was I used the droplet, a picture from the droplet combustion video to bring out the idea of equilibrium versus rate controlled processes in combustion. Maybe I thought I'll start by showing you a video of droplet combustion. This is the video from which that picture was taken. There's also audio, good, yeah. I think you can clearly see the flame in this case, yeah, and along with the droplet, yeah. So I think this is a good picture to show. Just a couple of things I want you to notice. This is the droplet and the flame and the igniter, and what is shown on the side, the plot, is on the x-axis there is time, and on the y-axis there is diameter squared. The diameter sort of measured from the video processing of the image processing of the video. What I want to emphasize is that the droplet time is dependent on the square of the diameter. So that is d squared law, as it is called. This is one example of a combustion process where chemistry has no role. So the time goes as diameter squared. It simply depends on the transport processes occurring at the surface of the droplet, and the heat flux that the surface receives is dependent on the location of the flame, which again is controlled by mixing and not by reaction rates. Okay. Of course, there are a lot of other complex things that happen. For example, sometimes the droplet boils and then shows some erratic movement, and that is what you see as fluctuations in d squared, but the overall linearity of d squared versus t is followed. The other thing I want to emphasize is that some flames, or only ethanol flame, is non-luminous and it does not have an yellow color. Okay. All the other fuels have a luminous flame, an yellowish flame like a candle flame, and all these are kerosene, gasoline and diesel are mixtures of hydrocarbons with carbon number of at least 6 or 7. Okay. So these kind of and ethanol of course is a pure substance and has only 2 carbon atoms. Okay. So these other fuels have a tendency to coke or form soot. Okay. That's one more thing I want to emphasize, and therefore the kind of modeling approach that is required is dependent on what phenomena you are interested in capturing. If you want to get this, explain only the d square versus t and get an estimate of the slope of the line, then there is a certain kind of approach that will work. But if you are interested in kerosene droplets being injected into a complex rocket combustion environment where you are interested in understanding whether that system will go into instability or not, you require a certain kind of approach, or if you are interested in emissions from let us say a reciprocating engine using one of these fuels, then you have no option but to actually include some level of description of chemistry in your calculations to predict emissions, okay, because the emission formation is a kinetically controlled process. Okay. So, a hierarchy of approach is what is suggested when taking a modeling approach to understanding systems. Yeah. I just thought I will show this example, and because we discussed this in the morning. With that, I would like to move on to a demonstration of NASA CEA. CEA stands for Chemical Equilibrium and Analysis. I am sure participants from ISRO and DRDO are quite familiar with this tool and they must be using it on a daily basis. But for the benefit of the others, I thought we will look at a few example cases. Okay. So this is when you open the software, this is the first page that you see. There are different problems that are listed here, different types of problems that are listed here. You can calculate equilibrium states under a variety of constraints. So you can calculate equilibrium states with temperature and pressure fixed, that is the first option. The second one is with the enthalpy and pressure fixed, that is the H and P problem, and the third one is the temperature and the volume fixed. The fourth one is internal energy and volume fixed. Okay. We saw in the morning that the first law of thermodynamics applied to a mixture of fuel and oxidizer at a certain initial temperature and pressure. When you are interested in calculating the adiabatic flame temperature, falls either in one of these two categories. It could be constant pressure or constant volume. For example, if you are analyzing a rocket combustion chamber, you will assume that the pressure is constant, and if you are analyzing a spark ignited internal combustion engine, then you will assume that the combustion is happening under constant volume conditions. And under constant pressure and adiabatic conditions, the first law says that the enthalpy should be fixed. We saw in the morning that the enthalpy of the reactants must be equal to enthalpy of the products, and under constant volume conditions it will become volume is fixed and the internal energy is fixed. Okay. This is the constraint that comes from the first law. The second law constraint is that in the HP problem, that the Gibbs free energy must be minimized, and in the UV problem the Helmholtz free energy must be minimized. So the HP constraint comes from the first law, the other constraint comes from the combination of first law and second law. In fact, the software calculates the equilibrium states by minimizing the Gibbs free energy function using Lagrange multipliers. Okay. Instead of I think I will set up a problem. Let us look at the example case that we discussed in the morning, determining the adiabatic flame temperature of let us say methane and air mixtures at different stoichiometric values at let us say 3 different pressures, 1 bar, 5 bar and 10 bar. Okay. So I am assigning 3 different pressures. Calculation will be done at 3 pressure values, 1 bar, 5 bar and 10 bar. Okay. So this is what first you pick which problem you want to solve, then you fix the pressure because you have to specify a pressure. Then we move on to the second tab where you can specify the reactants. Well, there is already hydrogen and air, but let us try methane, CH4. Of course, you will have different versions. CH4 naturally occurring form is gaseous, but there is also liquid methane, okay, which somebody may want to use for a rocket calculation, for example. Okay. Well, you have 2 options, either to specify the relative number of moles right here, okay, but we will not do that. We will just specify the initial temperature 300 kelvins and 300 kelvins. Okay. The stoichiometry can be specified separately here, either as equivalence ratio or oxidizer to fuel weight ratio or percentage fuel, all are equivalent, but only that the numbers must be consistent. So, let us try equivalence ratio in terms of phi. I will pick one value for lean, stoichiometry and rich. Okay. I will do a quick recap. We first picked the problem, we have picked the enthalpy pressure problem. You can assume, let us say we are interested in determining adiabatic flame temperature for a combustion device which is going to operate at constant pressure with let us say atmospheric pressure with methane and air as fuel, let us say the open flame that we discussed in the morning. Okay. Then we assign pressure values 1, 5 and 10 bar just to look at the effect of pressure, and then we have picked the reactants. The fuel is methane, the oxidizer is air, both are at 300 kelvins. Of course, I have specified I can specify the relative amounts here so that a certain stoichiometry is maintained, but I can also specify the values here, which is what I have done. Let us run the calculation and see what we get. So, these are the results. The fuel is methane, oxidant is air. For a phi of 1.2, which is fuel rich, the oxidizer to fuel ratio is 14.36, which I think is I don't know how this can be made bigger than this. So, okay, all right, thank you. Yeah. Sorry, I think nice. Okay, good enough. You can zoom a little further also, I guess. Okay, it's much better. Yeah. So the fuel is so we have specified the 3 equivalence ratios 0.8, 1 and 1.2. 3 pressure values 1, 5 and 10 bar. Do not worry about the temperature, that is only a estimate of the temperature that is provided for an initial guess. Yeah. The reactants are methane and the oxidizer is air. These are the species that are considered in the equilibrium calculation. I have not gone into the details. Actually, you need to pick a set of reactions which are linearly independent and then make linearly independent so that all the species that you have identified can be the mole fraction of all those species can be calculated. Then you apply the constraint of enthalpy being constant and minimize the Gibbs free energy after that. Let us go to the results now. Yeah, this is the case with phi equals 0.8. Phi equals 1, we saw that the air to fuel ratio must be 17.16 in the example that I showed in the morning. So, this seems consistent. This is 21.54 because it is lean. Okay. And the calculation has run for 3 values of pressure. I gave 1 bar, 5 bar and 10 bar. Yeah, now I will do that. Calculation has okay, this is not easy to navigate. 1 second. Yeah. Yeah. So, is it okay now? Yeah. So, these numbers are expressed in atmospheres, therefore, it is a factor of 1.01325 smaller than numbers in bar. Okay. So, that is why it is this number that is slightly lower than 1, slightly lower than 4 and so on. So, let us look at the temperature values. At 1 atmosphere, the temperature at an equivalence ratio of 0.8 is about 1997 kelvins. This is something that I mentioned. As the pressure increases at the same equivalence ratio, the flame temperature increases a little bit because the extent of decomposition is lower, but the effect is not so significant once you go to very high values of pressure. So, you go from 1 bar to 5 bar, there is some change, and then the delta keeps going down as you go to higher and higher pressures. this is one thing. There is also the molecular weight of the combustion products that are available, which we will see will be useful for calculating, or which is required for calculating the characteristic velocity in a rocket environment. This is the product composition, the mole fractions of the product composition. Well, the point that I made, that the dissociation of CO2 is decreases with increase in pressure. So, you have more CO2 at higher pressures and far less CO at higher pressures at 10 bar compared to 1 bar. Similarly, for H also, which anyway was very small at 1 bar, but it seems to be absent. There is no H radical that is there at higher pressures. Okay, so dissociation is limited. Well, there is also some NO, but remember that these are equilibrium NO values. NOx formation reactions are generally slow. So, this is how much NOx you will have if you allow for very long time. Okay, but in a real system, it is important to actually take into account the residence time for NOx formation, because the reactions are not as fast as the oxidation reactions. So, these are probably can be considered as the upper limit of the NOx that will form in these systems. And let us see, this is the phi equals 1. Phi equals 1, the O by F must be around 17.2, which is the case here. When I calculated, I did not take into account the traces of carbon dioxide and argon present in the air, that is why I got 17.16. Here those things are taken care of, so that is why it is 17.23, it is a small difference. Okay. So, we expect that phi equals 1, that the flame temperatures are higher than at phi equals 0.8, and which is the case. We have gone from 1997 kelvins to about 2200, and as expected, the flame temperature also increases with increase in pressure. Okay. There is some NOx, there is also some oxygen. I just want to look at the rich condition, and of course, the temperatures will be smaller as we expect. Let us just look at the NOx value at rich conditions. The temperatures are lower as expected. Let me not spend too much time on that. The NOx, the NO is much less than what it was at 0.8. Okay, so there is no oxygen available. See, the reactions are slow. I mean, even when you allow it to equilibrate, there isn't much oxygen that is available for NOx to form, because the conditions are already fuel rich. Okay, I think that is probably the only takeaway from this calculation. Well, there are a variety of things that you can do. You can do a rocket calculation and get the C star values, the molecular weight, and you can even simulate quasi one-dimensional isentropic flow through a nozzle to estimate for a given area ratio. You can estimate various things, assuming frozen equilibrium and frozen conditions or equilibrium conditions, which I will will discuss briefly tomorrow. But what I would like to go from, I can do many more examples, but probably it's going to be a little bit monotonous. But what I would suggest is that if you can give me some cases which you want to be analyzed, we can look at that. For example, some fuel oxidizer combinations from liquid rockets or solid rockets. There are some combinations that you want to look at or have some specific questions, we can discuss that.
We can take an example with 65 bar member press, the rocket calculation.
You want to do a rocket calculation? Okay, why not?
Tomorrow we can do.
No, let's do. It's okay. Yeah.
Member press is around 65 bar.
Okay. Just
yeah. If I have nozzle with some area ratio, specific 10.
Okay. Just correct me if I'm putting the numbers in the wrong place. Yeah.
Subsonic is, I didn't get. So we put one or it's a throat. No, it's a throat. Sonic is a throat.
Okay. So I should delete this, right?
Or we can put one.
All right. Okay. Fine. Let's see what it means. Yeah. And
one One more thing was there, estimated temperature that I didn't get.
See, that is only an initial guess that the code starts with.
It's not calculating.
It starts iterating from that number. Yeah, you can, giving a closer number will make the iteration process faster. That's it. There is no significant advantage beyond that. Yeah.
Rule I have liquid hydrogen and liquid hydrogen.
Okay. What is it? 100 kelvins? No. Liquid hydrogen. No, you are interested in the thrust chamber or what happens later? In the thrust chamber?
At the exit of nozzle, what will be the condition? Total also it will be.
No. The reactant condition at the inlet to the rocket thrust chamber would be gaseous hydrogen. Yeah. Yeah. So instead you want to simulate the real condition. At the entry to the thrust chamber, it will be in gaseous form at temperature that is less than 100 kelvins.
We should take 20 just inlet to the thrust chamber.
Inlet to the thrust chamber is after the cooling. That's the point I am trying to make actually. It goes, the film cooling, regenerative cooling happens and then it enters the thrust chamber. So, shall I make it gaseous hydrogen at 100 kelvins is the point that I am making. Yeah. Okay. And liquid oxygen. Happen to remember the temperature? Sorry? 80 kelvins. 80 kelvins is fine? Okay. And mixture ratio?
5.7 or something. 5.7. 4.8. 5.7.
Alright, let me see. Oxidizer to fuel weight ratio will be same as mixture ratio, I guess. Yeah. Give me some numbers. Okay. This is the optimal, this is the nominal. Yeah.
It's operating number.
Yeah. You want something less and something more. Let's say 4.5 and 7. 6.2. Okay. Let me see if it runs. It is unhappy with the data set. For logs, for LH2, the temperature range is a little limited. I will give a little higher temperature. All right. Let's see this. 80 is also 90.17. Yeah. Okay. You want me to print it or you want to look at, want to add some more conditions? What do you want to look at?
Temperature, whatever temperature we are getting, and also the composition species.
Okay. All right. This is for 5.7. Are the numbers visible for you? Actually, I shouldn't be looking in the other direction. Yeah. Starts from 64. I am guessing that I have given the AE by AT correctly. So, it starts at 64, at throat it is 36. Well, this is for the AE by AT of 1. There is no expansion. I think we should look at this case that the exit pressure is 0.86. Yeah. Ideal, this is the optimal expansion case I am guessing. So, the temperature is 3475 kelvins. C star is, it's in, okay, I didn't change the units, it's in feet per second, 7700, yeah. So 5.7, the C star is 7700. Which condition is this? This is also 5.7. Okay. Oh, okay. I think one is frozen, the other is equilibrium, probably. This is 4.5. Your temperatures have gone down, it is 3200. The C star would have also gone down. Of course, that is the C star comes down straight. Now, let me ask a different question. You have, let us say you have got a temperature from here, you have got a C star from here. Let us say you want to do further calculations. How do you decide that this number is a good approximation to work with? As in, this is an equilibrium calculation and you want to use it for further calculation. The question that I would like to pose and discuss is, how do we decide that the reactants would have reacted and reached a state that is sufficiently close to equilibrium before the expansion through the nozzle starts? That is an important question to ask and discuss. Yeah. How much time do you think it requires for hydrogen oxygen system to reach equilibrium? And how much time is available in an actual rocket engine?
So we will be having maybe 4 times the real record equilibrium, 4 to 6 times.
And how do you get an estimate for the time?
For the reaction time.
What is the typical reaction time for hydrogen oxygen? Yes. No, unless we know that, we cannot decide whether there is sufficient time. Of course, the time that is available for the reactants inside the combustion chamber can be calculated from the an approximate velocity with which the reactants move, enter inside and move through the combustion chamber, and length divided by that velocity will give us a good estimate of the time that the reactants spend inside the combustion chamber. And the way the injectors are arranged, it will also be a reasonable approximate assumption to make that the reactants are sufficiently mixed at a certain distance downstream, which we can subtract from the length of the combustion chamber. So, from that, starting from that point onwards, where the reaction between hydrogen and oxygen starts, where it is injected in a coaxial fashion and it reaches the nozzle, how can we be sure that it has reached equilibrium? So, is my question clear? Yeah, yeah. And this is routinely used for calculation, and that is the reason why I want to discuss this. Yeah. Let us start by getting a simple estimate for the time that is available in a rocket engine.
Suppose we have an injection velocity of around 40 to 50 meters per second.
Okay.
And the mixing length scale is the combustor is L, it's maybe some L minus 90% of L.
90% of L. What?
10%.
Let's take a specific engine. What is the length?
If we take one of the engines, maybe some 500 to 600 mm.
Let's say 500 mm. Okay.
Then the mixing length will be approximately from 40 to 60 centimeters. 40 to 60.
Fine. Take it as 500 millimeters. Yes. A number that is easy to work with. Yeah. Half a meter. Yes.
After that, we will have a mixing zone. The atomization mixing zone.
Correct.
Then coming to the reaction zone.
Yeah.
There we will consider almost like whatever we are discussing, like very infinite reaction rate.
Very fast reactions have happened. So
then coming to the equilibrium establishment, from there we will have nearly 1.5 times margin for attaining the equilibrium.
What is 1.5 times the margin? I am trying to estimate a time.
So suppose if the entire combustion reaction is taking nearly some 250 mm.
Right.
At 250 mm, entire
so the length available for the reaction, you would say, is 250 millimeters.
Yes.
And what do you think is a good estimate for the velocity in that region? The axial velocity in that region.
The axial velocity we will take 0.
No, you will take 0.
Okay, yes.
That's fine. Because you want to assume that there is large time available for the reaction step. Happening in reality, how much would be the velocity?
It depends on the temperature that we are really getting it.
Yeah.
And from that, using kinetic theory, we will calculate what is the molecular velocity.
You don't need the free molecular velocity. What we need is simply the mass flux at a given section divided by the cross section area divided by the density. So that you would say is 100 meters per second, 200 meters per second, or how much is it? Yeah.
I'm not in the
Is 100 meters per second a good value? Fine. So we have,
P200.
so 0.25 meters is the distance that is available and 100 meters per second is the velocity. So 0.25 divided by 100 is the time that is available, and that is 2.5 milliseconds, correct. So it's 2.5 milliseconds sufficient for a mixture of hydrogen oxygen to reach equilibrium.
Yes,
Why?
because the laminar flame speed for these conditions is very high. That is,
Okay.
if we are pressurizing the system chamber at 60 bar,
60 bar, okay.
and for the LOX systems at 1 atmosphere pressure on itself, laminar flame speed is 3.
Okay.
If you go to up to that high pressures, it will reactivity goes by square of pressure. So
Okay.
that means laminar flame speed is under root of laminar reactivity is laminar flame speed is under root of reactivity. That means laminar flame speed grow linearly with the pressure. So it will increase. Yeah.
Well, that analysis will show, if you assume the reactions to be effectively bimolecular, that the flame speed is insensitive to pressure. Okay. So that's one thing.
But yeah,
Even then,
it will be increasing.
even then, is the approximation reasonable?
Yes.
So if you, what number for reaction time would you get if we followed the same procedure that I described in the morning? I suggest that you please think about that. See, we have got one estimate for time, which is 2.5 milliseconds. The other estimate that we need to get is a time scale for the reactions to go to completion, which, as he rightly pointed out, can be obtained from an approximate value for the flame speed. Okay. Please plug in some numbers and see if this approximation that you regularly use to calculate equilibrium composition and use it for various things, expansion through the nozzle and various heat transfer calculations and so on. Is it a reasonably good approximation or not? It's something I would like you to go back and check, and we can discuss it next class, okay, or tomorrow, yeah. Okay, that's one good example that we have looked at.
So we have one recent.
Just before that, I just want to make sure, were you looking for something else when you post this question? Is that it? Okay, yeah.
Recently, we have been updating one of the rapid rates from 58 bar of chamber pressure, 52.3 bar to 64 bar.
Okay.
Just for increasing the thrust in the ISP. ISP remains the same, but thrust can be increased. In that context, when we are running the CEA, okay, this is one of the questions that we have been discussing for quite long time. The temperature was not quite there, not increasing, maybe from 4 degrees Celsius was increasing.
Yeah, as I mentioned, that the benefit that you will get because of lesser decomposition at higher pressures will saturate beyond a certain value of pressure. Yeah.
But the dissociation reaction that we have not considered that time, but after some maturity of understanding about the dissociation reactions, we really landed to the right number, maybe some 4 degree Kelvin when it was increased.
Yeah, I also would not expect that the benefit because of increase in pressure in terms of temperature would be significant, because you are going from already a pressure that is significant, that is sufficiently high to a slightly higher pressure.
The second thing is this increasing chamber pressure is the same mixture ratio. Obviously, mixture ratio only controls the temperature.
Yes.
Well, since it is not shifting much, we landed the same number almost.
Okay, yeah, some learning that you had. Okay, I just before we move on, I just wanted to, since the topic of C star came up, I quickly sort of went through that in the morning. I just want to, okay, so the point when the presentation loads, the point that I want to make is that for hydrogen oxygen system, the flame temperature will, like for any other system, will peak around stoichiometry, but the C star value, which is a parameter that is a measure of performance in an actual rocket, will peak at rich conditions, okay, because the C star is also dependent, or C star is proportional to the sound speed, okay. So smaller the molecular weight, larger is the sound speed, and the C star values will be much higher when you have large amounts of hydrogen because the molecular weights are significantly lesser than oxygen. So the as you can see from this, the flame temperature peaks at a mixture ratio of around 8, which is the stoichiometric mixture ratio for oxygen hydrogen system, but the C star, which is the dotted line, reaches a maximum at a mixture ratio between, I would say, is 4 and 5, okay, and I think that is a kind of number that is also used in actual systems, okay, where the C star is maximum, not necessarily where temperature is maximum.
Is this C star something with PC80 by m dot?
PC80 by m dot, and it is also proportional to square root of
So Van der Waals expansion.
square root of the temperature divided by the molecular weight, divided by the square root of the molecular weight. So it will peak. So as you can see, TF is maximum at 8, but molecular weight is significantly lower between 4 and 5 compared to stoichiometric values, and therefore square root of TF by square root of m will reach a maximum at rich conditions when there is lot more hydrogen, okay. Of course you cannot go further to the left of it, but at some point between 4 and 6 it reaches a maximum.